Can people online hear me?
Yes.
Okay, sorry to be late. I was looking at NMR data with a student and forgot about the class.
We need to open up a presentation on the screen.
Yes, I have to share first.
Yeah.
Looking for the share button. Say. There we go. Okay, I think we're in business. So we've talked about relaxation, and of course, in the Redfield theory, the critical connection between relaxation and the properties of the molecule come in the spectral density function. And we really haven't said very much about spectral density functions. So we'll start by talking about them today. And to remind you, I think I'm managing to go smoothly from having a cold to having hay fever. The spectral density is the real part of the Fourier transform of the autocorrelation function for the spatial parts of the fluctuating Hamiltonian. Remember, the spin parts go into these double commutators, and the physical part is here. And depending on the literature, first off, the autocorrelation function is even with respect to tau. So minus tau and plus tau are the same. So you'll see it both ways in the literature. And because it's even, we could either integrate from minus infinity to infinity or integrate from 0 to infinity and multiply by 2. Yeah?
So don't we have to use like a notation for the frequency in the exponential?
You mean here this omega?
Yeah.
Well, that's just the frequency. When we come to the actual relaxation calculation, we'll put in the frequencies that are needed for that relaxation mechanism. So this is just a general frequency. And then, as you saw from Anne, we can write these spatial terms as a part that depends on rotation, and we characterize those with the spherical harmonics, and then everything else goes into what I just called C here. I forget what Anne called it, but that'll be things like bond length, magnetic field strengths, chemical shift anisotropies, whatever's in the Hamiltonian that's not the rotation. And then, as you also know from Anne, we can do whatever frame transformations we need for the spherical harmonics using these Wigner D rotation matrices. I won't review any of that. So that means if we make that substitution, the spectral density function is now a kind of cross-correlation function between the spatial parts and the rotation parts. And in general, that's pretty difficult to calculate any analytical expressions. For example, if some loop in the protein, or if you have a protein that's a clamshell, I don't know where there. So the protein is doing this, opening and closing. Then, if we have two hydrogens, one in each part of the clamshell, when it opens and closes, both the orientation and the length of the vector connecting them is going to change. So both the C, which contains the distance for the dipole coupling, and the Y's that contain the orientation are going to be varying together, and that's going to be quite difficult to do a calculation of. So if one has to do that, that's almost always a computer calculation, not an analytic calculation. So for analytic calculations, we want to simplify. And the first simplification is that's made is that these spatial terms are independent of the orientation terms. And I just gave you an example where that's clearly not true. So this is the kind of approximation that may be good sometimes and bad other times. But you should remember the clamshell is an example where that clearly wouldn't be the case. And then, again, if we're not going to resort to computer calculations, there's kind of three simple assumptions that we might make about the autocorrelation function of the spatial terms. One would be that they're fixed, right? In which case, this is just the square of some fixed quantity. And that's relatively obviously simple. And that fixed quantity just comes out of the integral. The other assumption might be that whatever the time dependence is here is very slow compared to the time dependence of the Y's. And if that was the case, then this autocorrelation function of the Y's would decay to zero before the autocorrelation functions of the C's had time to decay. And in that case, we could say that this autocorrelation function of the C's could just be replaced by its initial value. And that would be the ensemble average of C squared. And then the other approximation would be that the autocorrelation functions of the C's decayed very quickly before the Y's changed. And in that case, the limiting value of this autocorrelation function would be the square of the average of the C. Because at long times, we would say the C's became uncorrelated, so the autocorrelation function becomes the product of C0 of T average and C of T minus tau average, but those are the same. So we just end up with the average squared. So here are those three approximations. If C is a constant, we just have C0 squared times now the autocorrelation for orientation, which is usually given a symbol capital J, and that's shown here. That's just the autocorrelation function of the Y's. Or if C varies very slowly, then we have the average of C squared, that's just the variance, is now a constant. And if C varies rapidly, then we just have the square of the average of C. So this, for example, the square of the average of C, we use all the time. If you say, for example, we're calculating relaxation of NHs, and we use a bond length typically of either 1.04 or 1.02 angstroms. Neither of those are the quantum mechanical bond length. If you look in a force field, the quantum mechanical bond length is something more like 1.01. But we don't want to pay any attention to the femtosecond bond vibrations and bending. those are way too fast to affect the NMR experiment. So we replace that with the average cubed squared. Right? The dipole coupling depends on R cubed. So this would be C naught here would depend on R cubed. So we have to average R cubed and then square
The, for a while at least, the preferred value for NMR was actually a little longer than the best fit value from X-ray, not shorter.
it. They are.
And if you were gonna run the average of R cubed, you'd think you'd get a biased average that's shorter. So if you average in R cubed space and then you back out, what does that mean R is? You bias short. And the argument was that that's because the angular fluctuations are more important than the distance fluctuations in that vibrational pre-averaging picture.
That's true. And the original calculation when Bax, Hay, Horshaw, Szabo published the first N15 relaxation measurement by 2D modern NMR, they used 1.02. And that later on, Dennis told me, was from just doing the averaging of the bond vibrations. And it was only later when Dave and Ad revisited the problem, Dave Case and Ad Bax revisited the problem, that they took into account the off-axis averaging from the bond angle changes, and that led to the longer distance of 1.04.
I think they were picking up on work by Yoshitake Ishii that he had already published this idea.
That could be.
All about it. I'm not sure that that's true, but
I don't know the exact fact, but yeah, Dennis told me that for reasons he couldn't remember, back in the original paper, they realized that there was this contribution from the off-axis motion of the hydrogen, but they didn't include it for reasons he couldn't remember. So anyhow, this part gets used, this assumption gets used all the time when we have to deal with femtosecond bond vibrations because they're modulating the coupling. So usually when you see quote unquote NMR bond lengths, they're not the bond length that you would get from quantum mechanics. They're averaged over fluctuations. Or you could say they're what you would get from a quantum mechanical calculation that included the fluctuations. This limit, where you have the variance, it comes up, although I'm told lots of times people don't worry about it, even though I use it as an example all the time. If you consider the NOEs to say a phenylalanine, and if I have two ortho protons, to see what I handed. So if I have two ortho protons, and then a third hydrogen somewhere, the distance to the two ortho protons isn't going to be the same. But you only see one set of ortho peaks typically, and that's because the aromatic ring is flipping, but they flip relatively slowly compared to tumbling. So that leads to this. The tumbling autocorrelation function has already happened, but you haven't decayed the autocorrelation function for the ring flips yet. So instead, you have to calculate the average of the 1 over r to the 6th distances, because the dipole coupling goes as 1 over r cubed. So you square it over r to the 6th, and then you average. You would average the 1 over r to the 6th distances for the phenylalanine ring. Here we're taking the average of the 1 over 3 distances and then squaring them in this other limit. This other limit would come up, for example, for a methyl group. You have 3 methyl hydrogens. If there's a remote hydrogen somewhere, the distance to each of the three methyls is going to be different, but the methyl group is rotating very fast. So you're going to see an average distance that looks like the 1 over r cubed squared distance. So, in principle, for example, in a structure calculation interpreting the NOEs to aromatic rings and methyl groups, those should be handled differently because of the difference in the averaging. Although I'm told by experts in structure calculation, it's not as important an effect as I think it is. Yeah.
Okay, so can we go back a little bit and explain why in the slow variation of C naught T we get whole squared of C naught?
So we look here at the autocorrelation function for C naught. If its decay is very slow, it never gets very far away from tau equals 0 before the decay due to the y's is over. So if this was, say, a 1 millisecond process, and this is 10 nanoseconds, we're done before this autocorrelation function starts to decay. So we might as well just set tau equal to 0, and then we have the average of C naught squared. And then the other limit, this is already decayed to whatever its average values are. Okay, so for a rigid spherical molecule, then we would just have the autocorrelation function for a sphere, and that's 1/5 e to the minus tau over tau c, where tau c is the rotational correlation time. Very simple. The 1/5, again, depending on the literature, that 1/5 might go into other prefactors. So you might see this written as just e to the minus tau over tau c. And in that case, the 1/5 is put somewhere else in the formulas. And then if we calculate the autocorrelation function and we transform this exponential, we get this very famous expression that J of omega is 2/5 tau c over 1 plus omega squared tau c squared. And again, where this factor of 2 appears could be different. You'll see this written without the 2/5, and then in which case the 2/5 is somewhere else. So that part, there's just a picture. The most important part of the picture is when you get to high frequencies, this is basically decayed quadratically. Right? Because if omega squared tau c squared is much greater than 1, this just becomes 1 over omega squared tau c. So we have a quadratic decay at high frequency. And then when omega squared tau c is much less than 1, right, this is pretty much flat. So if we have an ellipsoid, either a flying saucer or an American football, then there's 2 diffusion constants, one for diffusion around the symmetry axis and then around the other axes. And now relaxation will depend on the orientation of our relaxation Hamiltonian in the frame of the molecule. So the principal axis frame of the molecule is defined by the symmetry axes. And the principal axis frame of the Hamiltonian, of course, depends on what we're talking about. The dipole Hamiltonian, the principal axis is along the bond vector. For the CSA, right, if you have an axially symmetric CSA, then the vectors along the symmetry axis of the CSA tensor. So relaxation rates will depend on that orientation in the molecular frame. Relaxation will look different, for example, if we have a dipole pointing along the symmetry axis of the American football, as opposed to one in the transverse plane of the American football. So this problem, then if we have an asymmetric molecule like a potato, then there's three unique axes. Again, we can diagonalize the diffusion tensor, find the principal axis frame, but then there's a diffusion constant for the z-axis, the x-axis, and the y-axis, all of which are different. And that just becomes a much more complicated problem. But for the axisymmetric case, we have two diffusion constants, and then this is the equation for probability distribution. We have to go ask Mathematica or Claude how to solve this. The traditional way is to expand and circle harmonics or Wigner D matrices, and then work through term by term. I'm going to skip all of that. You can read it if you like. The end result is that we end up with the sum of three exponentials, and their relative weights depend on the orientation of our interaction in the molecular frame. So phi of 0 would mean you were pointing along the symmetry axis of an American football. Phi of 90 would mean you were pointing along the equator of an American football. So those are the weighting factors from the spherical harmonics, and then there's three different time constants depending upon the axes that you're rotating around. So this is quite nice actually for NMR, because for example, in a globular protein, if we measure N15 relaxation, we'll tend to have NH vectors pointing in many different directions. So if we have a crystal structure and we know the angles in the crystal frame, the crystallographic frame, and then we can figure out the rotation that goes to the molecular frame and get the diffusion constant. So it turns out to be a very powerful way to measure diffusion tensors, rotational diffusion tensors. If you do this by fluorescence, the other main way of doing it, you have very few probes. Here we tend to have lots of probes pointing in various directions. The one time this doesn't work very well, of course, is if you imagine that you have, say, a 4 helical bundle, then all the NHs basically point along the helical axis. And it becomes much more difficult to get this to work well. You don't sample the orthogonal directions very well. It's a similar problem that comes up with residual dipole coupling. If you don't have a quasi-uniform distribution of orientations, residual dipole coupling is also become more difficult to measure, to interpret. If we had the potato or an asteroid, all that would happen here is we would then have 5 exponentials for the autocorrelation function and just much more complicated equations for the time constants and the amplitude. Nothing fundamentally changes, just more exponentials. So there's the spectral density function for the ellipsoid. There's 3 terms. It comes from the Fourier transform. There's a cute trick from Raphael Bruchweiler that says if the asymmetry isn't too large, we're not too far away from being spherical, we can approximate either the 3 exponentials or the 5 exponentials by 1 exponential with an effective correlation time. and that gets used a lot. It's shown here, different analysis than from what Raphael did, but here for the axially symmetric case, I just did a first order Taylor series expansion, summed up the terms, and then said, well, that sum case also looks like an exponential, the first order of some exponential. So when I did that, here's the first order expansion of the exponentials. I can move the sum in. I substituted in, did all the sums, and I have something that's 1 minus tau, and I call all this other stuff an effective diffusion constant, and then say, well, 1 minus something times tau looks like the first order expansion of some exponential, so I converted it back to an exponential and define an effective time constant or effective diffusion constant. Raphael did it in a much more sophisticated way. You can read his paper, but here's just some example calculations for different degrees of asymmetry and different orientations in the molecule. And the approximation for moderate asymmetries is extremely good. So we in fact use this approximation a lot, just because it's much simpler to deal with a single exponential rather than 3 exponentials or 5 exponentials. So that's overall rotation. And then what about internal motion? So now the problem gets more complicated because we have to adopt the approach that Anne introduced, where now we have to transform to the laboratory frame the fact that there's some motion of our Hamiltonian principal axis system relative to the molecular frame, because the bond is moving around, and then the transformation from the molecular frame to the lab frame to account for overall rotational diffusion. In Anne's case, that second transformation would have been to account for MAS spinning, but now we have to, in solution, do it for overall tumbling. And that transformation gets done with the Wigner-D matrices. And now, again, it is very complicated. So a common approximation is that the internal motions are independent of the overall motion. And again, you can easily think of cases where that's not true. If you're talking about going from folded to unfolded, then there's probably, in the unfolded state, internal and overall motions are probably tightly coupled to each other. Even my example of the clamshell, maybe that's not true. The diffusion of the open clamshell might be substantially different than the closed clamshell. So one can think of examples. There's some work in the literature about trying to handle the coupling between internal and overall motions, but it's pretty complicated to do in the analytical theory, and again, often turns into a computer simulation. But if we make that assumption and we write out all the D's, we find there's still a little bit of complication, because if the molecule isn't spherical, the effective internal motions depend on the orientation of the Hamiltonian principal axis system in the molecular frame, even if the motions are independent of overall tumbling. And again, you can see that if you just think about, again, the American football, if you have an NH vector along the symmetry axis of football, and that vector is wobbling around, it's easy to see that that might have a different effect than if the symmetry axis is in the equator and now the vector is wobbling around. So there's still a coupling between the asymmetry of the molecule and the internal motions, even if they're independent from overall tumbling. And again, that's mostly because of the computer calculation. If overall rotation is isotropic, then we can factor this, and we have an autocorrelation function for overall tumbling, multiplying the autocorrelation function for internal motion. And that kind of approximation is used over and over again, even if we know it's not really true. So even for the actually symmetric tensor, you'll see in the literature that things are often written just as the autocorrelation function for the actually symmetric tensor times an internal correlation function, even though they should be coupled. Again, there's some work in the literature on improving this, but not a lot. Then the autocorrelation function for the internal motions, that is again just an autocorrelation function for the spherical harmonics for the internal motion in the molecular frame. If tau is 0, then the addition theorem of the normalization of the spherical harmonics is that's going to be equal to 1. So our internal autocorrelation function will start at 1, and then will decay to the average of the product of the autocorrelation function. It's the same argument. And this is called S squared in the literature, the generalized order framework. So that's true pretty rigorously, just based on the statistical properties of the spherical harmonics and the properties of autocorrelation function. We haven't said very much about the underlying motions yet. What happened here? Yeah. So, and we'll object, but I'll say that the motions that you're likely to study in solution NMR are overdamped. They're not harmonic anymore.
I don't object to that.
Okay. And
I look for pathological motions, but that doesn't mean they're every day.
so that means if we think the motions are overdamped, that they can be represented as a sum of exponentials. I've just written this down as a sum, infinite sum of exponentials. And then one can get into a thicket of literature about whether that sum can or should be represented by a distribution function with some probability distribution for the time constant tau sub I there, or whether this is an exponential representation of what's really a stretched exponential or some other complicated form. So I'm going to let you read all that complicated literature on your own. But if we just have a sum of exponentials, then our basic question is we can't measure by NMR an infinite sum of exponentials. How do we approximate this? So the most famous approximation was to say, let's just approximate this complicated set of exponentials by a single exponential. And you might have thought, since all I ever do is talk about Taylor series approximations, you might have thought that we should approximate this using a Taylor series approximation. And that would say that you had defined your time constant in your single exponential approximation by looking at the first derivative, right? That's the first step in the Taylor series approximation. And that was done in the literature, but it turns out not to be so useful. In that case, you're dominated by the very fastest motions. Instead, what Lipari and Szabo did was fix their effective time from the integral of the autocorrelation function, not its derivative. And that turns out just to be very useful empirically. I don't know if there's a deeper fundamental reason why you might have preferred one over the other. And we've done a little bit of work about what if you said I want an approximation that uses both, so that you were sensitive to both the fastest motions and the slowest motions. But anyhow, Lipari and Szabo said our single exponential approximation is going, the time constant is going to come from the integral of the autocorrelation function, and that's shown on the last line here. S squared is the limiting value. So if A0 was in my order equation here, A0 for us is the same as S squared. So this function has the property, when tau goes to infinity, we get S squared. When tau goes to 0, we get 1. And it's a single exponential with some decay. We could then multiply that by overall tumbling, because we were assuming independent of, so we could factor, and then Fourier transform. So here's the Lipari-Szabo model-free, so-called model-free spectral density function, and here tau prime ends up being whatever this is called, the geometric mean, maybe. So there's the picture. We have some orientation in the molecular frame, and then S squared is measuring the amplitude of the internal motion, and tau sub b is measuring the time scale of the internal motion. And this is a very simple decomposition. If you were just asking yourself, what's the simplest information I would want to know about the dynamics of some bond vector? It would be the amplitude of the motion and the time scale. And in this case, the amplitude is measured by the order parameter, which is related to the spherical harmonics, and therefore to the equilibrium distribution of bond orientations, or CSA tensor orientations. And the time scale is the time scale in the sense of this integral of the autocorrelation function. You might like to know more information. You might like to know, does this look like a diffusive process or a hopping process? But the NMR experiment in solution is not going to be so good about that. And maybe either has or will show you different simulations for hops and solid state NMR. And there you have more discrimination between mechanism and the solution NMR, amplitude and time scale. And we can write many models for the underlying dynamics that will give the same S squared. And that was one of the features of the original Lipari and Szabo paper, was they said there's too many different models being applied to NMR relaxation. Here's a general model that kind of encompasses those other ones without making a lot of assumptions about what the underlying mechanism is. Of course, that's perhaps not so helpful if you're really interested in the underlying mechanism. But these days, if we want mechanism, we mostly look at MD simulations to get ideas about mechanism, and the NMR to get the amplitude and the time scales, and then try to test the mechanism by mutation, etc. So here's just to give you an example, here are 4 exponentials, something that's the sum of 4 exponentials. And on the left, the exponential time constants are all pretty fast. Black is the exact calculation, and pink is a Pari-Szabo approximation. And you can see the approximation is pretty good. It overestimates in one part of the curve, underestimates in the other part, because it has to conserve the area. But if I make the time constants very different from each other, this doesn't work so well. As you can see here, now there's a very fast initial decay, and the approximation doesn't capture that. That was realized pretty early on by Floor and Szabo, and the solution was to just add another exponential. So now we have one exponential for very fast processes and a second exponential for slower processes, but still faster than overall tumbling. If we work out the 2 exponentials, we can manipulate that to look like order parameters again. I could have written this as A0 plus A1 times an exponential plus A2 times an exponential. But usually people manipulate this to look like order parameters again. So that's the expression. And again, now, if I show that graph, you can see this fits the 4 exponentials much better. There's now a term that can fit the fast decay as well as a term that can fit the slow decay. So probably at least 3/4 of the relaxation data on proteins are analyzed with one of these 2 functions or slight variance. There's other approach, and that's in part because you just run out of data. Particularly this limitation that once you get the high field, the spectral density functions are all decaying as 1 over omega squared, limits the information content available. So this 2 exponential equation plus overall tumbling is enough to fit most high field data. Fabian Farage in Paris has rekindled interest in relaxometry, trying to go to much lower fields. And the point of that is to actually get out of this 1 over omega squared regime, to get to the part of the spectral density function where it's actually rolling over and starting to become flat, in the hopes that there's more information available there. And then, of course, if we have S squared or tau sub b, again, we might wonder what models we would apply. As I said, frequently these days, one uses computer simulations to help with this. But we can write down the average of the spherical harmonic that depends on the equilibrium distribution of orientations integrated with the spherical harmonic. Here's probably the most famous example, diffusion in a cone. The vector can move freely within a cone, but it can't leave the cone. And if we just do the integrals, S squared is the simple function of the semi-angle of the cone. So we can take S squareds and transform them into semi-angles and get an idea of how much angular fluctuation there is in the given bond vector that has some S squared. Or you might think, I think it's more fluctuations around some dihedral angle. So now I'm on the surface of a cone, and maybe I can't go all the way around the circle because there are barriers in the dihedral angles. So what happens then? So here's the potential function for fluctuations in the dihedral angle. in which you're restricted to kind of a single well with some functions. There's no hops here. And this is called the von Mises distribution. Again, we can do the integrals and get an expression for S squared. Here are some pictures. So the black line here, here's the probability distribution. The black line is there were no barriers. I can just go all the way around the dihedral angle. The blue is sort of restricted and the pink is even more restricted. And then here I'm showing S squared as a function of how restricted we are. And obviously S squared goes down as the restriction lessens, so there's more sampling of angular space. Black is the diffusion in the cone, and then the pink is this von Mises distribution that eventually just becomes free diffusion around the surface of the cone. So variants of these are used quite commonly just to get an idea of how much motion we might be talking about. Because none of us have much of an impression of what, an average of a spherical harmonic is. So these are kind of heuristically useful. The correlation times are even worse to try to interpret. So for example, for diffusion in a cone, the effective correlation time can be worked out. It's a quite complicated function of the cone semi-angle. So it's much less common to see people try to interpret the tau sub e's with some analytical expression. If you wanted to try to interpret tau sub e's, that's almost always goes to a computer calculation. And these days agreement, I would say, is semi-quantitative, not really quantitative. Here's just again a simulation showing diffusion on the surface of a cone and
That was in the cone, right?
within a cone, diffusion within a cone, and
So when you do that, as it's a diffusion, is it kind of flat, like you're filling the cone equally, or is it more of the way that you're setting this up, or you setting that up with a?
to the best of my abilities, this was a random walk on the surface of the cone. It's not flattened.
And it's not like preferring the center.
No.
In a sense.
No.
Okay. And for-
It's flat within the angular region.
And traditionally, when people fit those with a Lafarge angle, it's the same, right?
Yes.
Equal probable all over, and it's like you had empty space.
Yes. Yep. Rigid walls and no barrier in between. So you can then see the fluctuations in the angle are restricted, and there's the diffusion of the cone calculation, and then the simulation. The other approach would be to use what are called jump models. So this is essentially a kind of chemical kinetic strategy. We have a bunch of sites. Each site is characterized by a set of Euler angles and the probability of occupying that site, and then rate constants for jumping from one site to another. So again, we can write down the autocorrelation, the order parameter, we can write down an expression for the autocorrelation function. And these can be analyzed by a very standard approach. We write an expression for the probability distribution. This matrix R has all the jump constants in it. We're going to solve for the probability distributions and then just integrate up all of the terms to get the autocorrelation function. So the standard way to do this is to symmetrize the matrix and then find its eigen decomposition in terms of eigenvectors and eigenvalues, and then plug everything in and do a bunch of algebra, and you end up with a general result that depends on the spherical harmonics in the different sites, I and J, and then the populations of the I and J sites, and then an exponential term that's an eigenvalue summed over all the eigenvalues. So this looks perhaps a little complicated, but for a computer, this is very easy. So given the matrix R, or the number of sites and given rates, the computer can do this calculation very easily. Or going the other direction, I have the relaxation data, and now I want to go back to the jump model. You're limited as well to how many terms can be fit, right? Each of these exponentials, when we Fourier transform, leads to another Lorentzian term in the in the spectral density. So we're limited again by how many terms we can possibly fit. It's pretty simple for a two-state model. We just have to, here's the matrix R, here it is symmetrized, here are the eigenvalues, here are the eigenvectors. All of this we can get from Mathematica or ChatGPT. We do up all the sums. Here at the end of the day is the two-site jump autocorrelation function, and it turns out to have the form of the Loparizamo function quite conveniently. And we have an order parameter. The order parameter is the population weighted average of the two orientation. And KEX is the sum of the jump forward and reverse jump rates. So it's almost an expression you could have imagined writing down a priori. Okay, that's the end of the first part of today. So let's take a 5-minute break, and then you can ask questions before we go on to the second part. I can finish my coffee. So autocorrelation functions and spectral density functions, of course, have a very central role in statistical physics. But in solution NMR, you might say they're a little boring because the autocorrelation functions are just sums of exponentials, and therefore the spectral density function is just the sum of Lorentzians. And the interesting part is, given some NMR data, how do we go backwards to learn something about the molecule? So that's more about how do we analyze experimental data to get the most information out. The forward problem of giving a model transforming a bunch of exponentials isn't so complicated, right? And not so terribly interesting in a way. So eventually we'll talk about some actual experimental issues of trying to learn something from relaxation, but not today. What I want to do today, in part to get you ready for your next visit from Ann and then from Hashimi, is then talk about slow processes. We've talked about relaxation in the Ridgefield limiter fast limit. But if we go to chemical exchange or conformational change, protein folding, base flips in DNA and RNA, now we could be talking about processes that are slow enough to violate the assumptions of the Ridgefield theory. And then we need a new theory. Because it turns out the phenomenology is quite interesting. So here's a simple example of a chemical reaction in which A plus C goes to B plus D. And a very important simplification in NMR is, of course, in the reactants, the spin is either in A or C. It can't be in both A and C at the same time. Spins aren't divisible. And similarly, after the reaction, the spin is either in B or it's in D. So most of the experiments you're likely to do, the system is going to be at chemical equilibrium. And that means that we can simplify this equation by defining so-called pseudo first order rate constant. So if the spin of interest is in A and we're equilibrium, the concentration of C is a constant, and we never observe C because our spin is never in C. So I can define a first order forward rate constant as being the real rate constant times the concentration of C. And similarly, if in the products the spin of interest is in B, it's never in D, and I can do the same thing for the reverse reaction and define the pseudo first order rate constant as the true constant times D, concentration of D. So that means all of my problems have the functional form of this first order relaxation rate. So I just have to solve one problem and I'm done. So if I forget about the primes, remembering I might have to sort out the pseudo first order rate constants, the chemical problem looks like DADB is this rate matrix times A and B. So minus K12 means that I lose molecules from the A state. Here, where do those molecules go? They go to the B state. Here I lose molecules from the B state, and they go to the A state. This is exactly what you were written down starting in high school. Maybe not in matrix notation in high school. Now the rate matrix turns out to only have two eigenvalues. One of them is 0, and the other is the sum of the two rate constants. And that's why KEX, the sum of the rate constant, comes up over and over again in these problems because there is no other real time constant. It's just the sum. The 0 means that there's an eigenvector that will tell us the equilibrium population. But you already knew that. If I set this differential equation equal to 0 and solve it, I'm going to get the equilibrium populations, because then dA is equal to 0 and dB is equal to 0. So you already knew that. It's just a fancier way of saying it. And now we can write down for the longitudinal magnetization what are called the Bloch-McConnell equations. McConnell was my scientific grandfather. My graduate advisor was a postdoc with Harvey McConnell. So we have the kinetic rate matrix just added to the relaxation rate matrix. Those spins that are in site 1 lose magnetization from their own relaxation process, and because they jump over to molecule 2, and vice versa. This bit at the end ensures that we relax to the equilibrium distribution. PA and PB are the equilibrium populations of the two states. We can change the form. We can write them in a form that's easy to imagine more dimensions. The matrices just get bigger if we have 3 states rather than 2 states. And they all have a formal solution in terms of the matrix exponential. And the matrix exponential is again a matrix. So these are called various things, maybe transition matrix elements or transition amplitudes.
What are the units? Like, we can't think in it for this.
Well, these are the matrix elements of this. So what are the units in E to the RT?
Doesn't have any unit, right?
They don't have units, right? R is a rate. Rate times the time is unitless. The exponential is unitless. So these things are unitless. They're just the matrix elements of the matrix. So, and we can write them down for 2 by 2 matrix. You can just ask Mathematica or ChatGPT what the actual matrix exponential looks like. But here's the phenomenology. So if there's no exchange process, no jumps happening, and I invert the A spin, we expect us to see recovery back to equilibrium with R1 of the A spin. But now if there is a jump process between them, then recovery of the A spin becomes bi-exponential. And now you can see that there's initial transfer of magnetization to the B spin, and then eventually it relaxes back to Boltzmann equilibrium. And that's basically all the phenomenology there is. Things get much more complicated if we talk about transverse magnetization. Because now we have the frequencies of the 2 spins. I don't remember what comes next. Now, if you wanted to calculate the spectra associated with this matrix, of course, you could just go and ask Lon to integrate this differential equation and then Fourier transform the time dependence to get a spectrum. That would be very similar to how things work on the spectrometer. Just because it's good for your souls, I'm going to show you a different way of doing it. That would be kind of classical mathematical. But there's nothing wrong with the brute force in the modern computer era. There's nothing wrong with the brute force method of numerically solving this differential equation and then doing a Fourier transform. So here's the equation, and I put some symbols in it. And there's something called the Laplace transform. We use the Fourier transform a lot. Here's the Laplace transform. It's the integral from 0 to infinity of our function times the decaying exponential. Or the Fourier transform, this was a complex exponential. Now it's just a decaying exponential. And it has the simple property for the derivative. The Laplace transform of the derivative is just this integration value, constant variable s, times the Fourier, times the Laplace transform of our function minus the value of the function at time 0. So that means I can take the Laplace transform of both sides of this equation and use the derivative property to replace the derivative. And I end up with this equation where the s is to remind me that this is the Laplace transform. And this is just an algebraic equation. So the Laplace transform is converted the differential equation to an algebraic equation. And I know how to solve the algebraic equation. So here's the algebraic equation. I need the inverse of the matrix and the value of the function at time 0, that's trivial. And then I have the Laplace, the answer in the Laplace domain. Now the difficulty with Laplace transforms is that it can be hard to find the inverse transform. But in this case, we don't actually need the inverse transform. We can use a trick and substitute s by I omega. And when I do that, I have something now that looks like I'm in frequency space, which is where my spectrum is. And then I need to sum all the columns. My spectrum is going to have the contributions from A, B, species A, species B, species C. So this just does the dot product, give me the sum. So here is my spectrum. It's the inverse of a diagonal matrix, I times omega, minus my matrix R. I take the inverse and then do these two multiplications. So that's very simple. Doing the matrix inverse takes a computer a tiny fraction of the time it takes to calculate the matrix exponential, which is what you would need to solve the differential equation. So back when computers were slow, this was very important. Now the computers are fast. Maybe this isn't so important, but it's important historically. Anyhow, here's what we get. If there's no jumps, we just see two NMR spectra. One line for the A state and one line for the B state. Now, before we go on, let's come back to this matrix here. If there's no exchange, right, we just have recession at the A frequency and decay with the R2 of the A state, and similarly for the B state. Now, suppose there is exchange, there are jumps, but K is very small. The jumps are slow. What's the effect going to be?
You still see two peaks.
You still see two peaks. But what happens to their lag? What I mean by slow, what I mean by slow is slow compared to the difference in the chemical shifts. The no exchange case, where I just see decay with R2 and precession with omega A. Now I have very slow jumps. And by slow, I mean much less than the shift difference between the two states. The lines are going to be broadened, but exactly by how much? You can look at that matrix and tell me the answer. I told you there were only two fundamental principles about relaxation. One of the two applies here. Yeah. The perturbations are much smaller than the shift difference. What do we say? What approximation can I make to that matrix if the jumps are slow?
I'm sure I'm going in the right direction, but does R2 is equal to the variance times the correlation time? That was one of the principles.
That's the fast. That's the other end, right? The other end is when the process is fast. Then we get the adiabatic part is variance times correlation time. And the other limit, so what was the other main principle? The secular approximation, right, which says that
if we must have a degenerate frequency in the interaction frame in order to see the cross relaxation.
right. So here, if the shift difference is large relative to the jumps, the two lines are going to be non-secular. And then what happens to cross relaxation? It can't happen, right? That's what Krishna just said. So if there's no cross relaxation, what can I do to that matrix? Which terms in the matrix represent cross relaxation? The off diagonal element. So if the jumps are slow, I can put the off diagonal elements to 0. And then how much broader is the A state line? Its effective relaxation rate becomes R2A plus K12. And the B state becomes R2B plus K21 is the effective relaxation rate. So you expect the lines to broaden, and they broaden by the jump rate out of that state.
Which is interesting because we usually talk about it being the sum of the two rates that can't be disentangled, but in this little limit, maybe you can.
Yes. And jumping back is ineffective because the rapid phase evolution in the other state means you jump back with a random phase. and those random phases of cancel over the ensemble. Right, that was my picture of the vectors getting anti-opposed to each other. So we know this limit. We know the first thing we're going to see is broadening of the two lines. And the amount of broadening is by the jump rate out of each state. So there we see it. One of the things that's interesting, of course, is if the populations aren't equal, suppose the B state has a lower population, the jump rate out of the B state is larger than the jump rate out of the A state. So the minor state is preferentially broadened. So that makes it very hard in NMR to find the minor states, because their integrated intensity is the population, but their width is proportional to the jump rate. So suppose in, I don't know what my numbers are here, but suppose the minor state had a 10% population, the jump rate out of the minor state was going to be more or less 10 times that of the jump rate out of the major state. And therefore, the minor state would be 10% the integrated intensity, but 10 times broader. So it's going to be a very broad, short peak and really difficult to find. And the people in Hashim's group know that we generally don't try to find them by just looking for them in the spectrum, right? Because we don't see them. They're what's called the invisible peaks. We find them in another way. And this is why. It's because it's just not that they're 10%. If they were simply 10%, we could find them. 10% and 10% broader, or 10 times broader, that's a quite different kettle of fish. Well, eventually, as we make the exchange rate larger, the peaks start to shift a little bit, but then they merge and become very broad. This is called coalescence or intermediate exchange. Mostly when this happens, the peaks are gone, you just can't find them. And then you have to play around with conditions to get them to come back, maybe changing the temperature or some other condition. And then we start to see them grow in at the population average position. When they appear at the population average position, that means we're in the fast limit again. And in the fast limit, what's our expression for the line width? Or for the R2, right? That was our other principle. Yes. So variance times time scale. The time scale has to be 1 over KEX. That's the only time constant. And then we just have to calculate the variance for a two-site hop, which you did in the problem set. So here's what we know from our two principles. In the slow limit, each site is broadened by its own jump rate out of that site. And in the fast limit, we see the population average, and we get the contribution to the line width that's P1, P2 delta omega squared. That's the variance over KEX. That's the correlation time. So we know the two limits. And in between is mostly a computer calculation. There are approximations in the literature, but it's mostly a computer calculation in between those two limits. Again, we said back in the beginning that if in R2, was just dephasing, if we could pulse fast enough, we should be able to refocus the dephasing. And that, of course, is the Carpenter-Gill experiment, where we have a string of spin echoes, and we hope we can make the time between the pulses more or less the same time scale as 1/KEX. So we can write down what this looks like mathematically. That's just all shown here. And again, it's a compute, it could be a computer calculation or an analytic calculation. This problem has been solved for 2 sites. And then there are approximations for more than 2 sites. But again, most times these days, this would just be a computer calculation. And if we do the experiment and measure the rate constant as a function of the time between pulses, that's called a relaxation dispersion experiment. And then by looking at that graph, we hope to learn what the rate constants were. One thing to be careful of when you're reading the literature has no fixed rule about whether, as shown here, the time between 180s is tau CP, or whether that's 2 tau CP. So you have to read what the authors mean carefully, because I could easily have written this as tau CP over 2, 180 degrees, tau CP, 180 degrees, tau CP over 2. So there can be a factor of 2 difference from paper to paper as to how tau CP is defined. And you just have to be wary of that. So here's some data. Early on, it's one of these things that the pioneers of NMR knew, and then everybody proudly forgot. So the Carver and Richards paper has analytic expressions for the 2-site jump case for CPMGs. So the equations that are used for fitting, the analytical equations that are used for fitting, are frequently the Carver-Richards equations. But buried in that paper, they said, back at a time when there were no high field magnets, they said, of course, this all varies as omega squared, as we see from our fast limit expression, and doesn't vary with omega squared in the slow limit, because we just depend on k's. So the magnetic field dependence should be interesting. And that was all promptly forgotten until we started collecting these data on VPTI and realized that having more than one field was really helpful in interpreting the data. So you can see, for example, at for cis38 at 310K, if you look at the y-intercepts, the scaling is almost the ratio of 500 over 600 squared. So if we collected data at 500 and at 600 megahertz, if we're in the fast limit, we should be scaling by the ratio of delta omega squared, so 6 over 5 squared. And that's almost what we see for cis38 at 310.
Fast limit, the prediction is scaling by delta omega squared.
Yeah.
Slow limit, the prediction is
No scaling.
nothing whatsoever.
Yes.
We're about to try to use the same thing for solids NMR, which we haven't done before that much, maybe with model compound, to break a problem with the ACSA fitting better.
And you can see an example for arginine 39 at 300K. You can see the y-intercepts are almost independent of the size of the magnetic field. If you look at ARG 39 at 310, I mean, that's where we had the data originally. If we only had data at one field, you could see we could almost fit a curve that looked like cis 38 to the data. Right? There's a very small kind of hump in the fitted data for ARCH 39 and 310. If the fit was the equations that the fast limit equations, they don't have that kind of hump, but we would get almost the same fit at one field. And in fact, when we first published the data, when we were developing the pulse sequence, that's what we did. We just had data at one field and we fit the fast limit equations. The fit wasn't quite as good for the arginine as the cysteine. But in my usual history of having come from fluorescence, I muttered something about the low signal to noise and NMR spectroscopy. And we published the paper on the pulse sequence. And then shortly thereafter, we realized that there was this magnetic field dependence. And once you have two fields, you actually can't fit the arginine 39 data anymore with the fast limit equations, just because it doesn't scale quadratically with the field anymore. Even though at one field it looks okay. And you can see cis 38 at 300 is somewhere in the middle. It's not fast, but it's not really slow, and arginine 39 now is quite slow. One of the things about the fast limit equation right here is there's really only two parameters to fit: the variance and KES. We can't really separate the variance parts into delta omega and the population. But once we're not in fast limit, then the equations separate the populations from delta omega. So actually being out of the fast limit has more information content than being in the fast limit. So we would actually now try to manipulate the system, changing the temperature, etc., to try to get out of the fast limit. This equation also tells you another shortcoming of the CPMG equation, and that's that you're only dependent on the square of delta omega, which means you don't know the sign of delta omega. So if you see the major peak, you don't know whether the invisible minor peak is above or below the major peak. You have to try to figure that out from other experiments. Srinakoff and Kay have an elegant way of doing this by looking at the difference in peak positions for HSQC and HMQC experiments. Because the HMQC, you have multiple quantum coherence, and the exchange process influences the multiple quantum coherence a little differently than it does the HSQC single quantum coherence. So that can help you decide the sign of delta omega, add into a CPMG experiment. Not knowing the sign can be pretty dramatic effect on the data if you're having to guess the signs from chemical trends, because you can be quite wrong. So always try to know the sign of the delta omegas, and you'll see in a moment that's what made R1 rho and CES experiments so popular. Yeah, so then the other approach is to turn on the B1 field, what's called R1 rho. And this is just to remind you that now we have a new frame. We have this tilted z-axis. This is the vector sum of the offset and the B1 field. So in fast exchange and the fast limit, we can apply the Redfield equation. And we just have to do a frame transformation to get into this tilted frame rather than the laboratory frame. But we can crank through the double commutators and the spectral density function. And here's the result. We have the sine squared theta dependence because of the tilt angle. And then we have a dependence on the jumps and on the strength of the omega E field. So in the R1 row experiment, we're going to change the omega E field either by changing omega 1 or by changing the offset. Either one works. And then we'll try to fit. There are two states. We get this, sine squared theta PAPB delta omega squared KPX. So we have the same problem in the fast limit. We can't separate PA and PB from delta omega squared. And we only have delta omega squared. So again, we don't know the sign of delta omega. There's the fast limit again. As I said already, when we're not in the fast limit, the Taylor series doesn't much help. And we're back to looking at the Bloch-McConnell equations. So again, we can just numerically calculate these results. We can put in what we think rates are, calculate the decay, calculate fit the resulting decays, get the apparent rate constants. So there's plenty of software programs around that will optimize values for the chemical shifts, the rate constants, etc., just by brute force solving the Bloch-McConnell equation. Modern computers are very fast. And I mean, the good thing about using the Bloch-McConnell equations is that if you decide there's some other effect that you need to take into account, then you just have to expand the matrices. So it's convenient in that regard, as long as you have a big enough computer. But sometimes, well, here's just what this all looks like. Before we had for a 2-site jump process, we had a 2x2 rate matrix, and we could solve that analytically pretty easily. But now we have to keep track of X, Y, and Z magnetization in the tilted frame. So for 2-site jumps, we now have the 6-dimensional rate matrix. And the 6-dimensional matrix doesn't have analytic eigenfunctions and eigenvalues in the general case. So we can't write down, except for special cases, we couldn't write down a solution even if we wanted to. All we can ask if we want an analytic result is there an approximate solution to this problem? And this just tells you.
What if you were in a subspace, so the transverse is just one complex number, or the Z is just one, you say those are not going to exchange?
Right, but once you turn on the B1 field, they're coupled together by rotation under the B1.
With the B1 field, you're
Yes.
Yes. Free precision.
Yes. So Oleg Trout, when he was a graduate student, had realized that this 6-dimensional matrix has 6 eigenvalues, but 4 of them represent rotations orthogonal to the spin locking field. There's I plus for the A state, I minus for the A state in the tilted frame, And those tend to dephase very rapidly, both from what's called R2 row and B1 inhomogeneity. And then there's two eigenvalues that are along the Z prime axis. But one of those will decay away rapidly, basically at the sum of K1 plus K2. And the other one will decay away slowly. And the one we're interested in is the slow decay. The fast decay happens very quickly. We don't see it usually in the experiment. In fact, we once wasted a lot of time trying to measure it. But the slow decay, then there are approximations for it. Because now you're looking for slow decay means that negative eigenvalue is close to zero. And now there are approximations.
So that approach is kind of like going into the spin law frame.
Yes. There is a
Or
spin law.
everything that's not commuting.
You discard everything that's not commuting, and then you say, what's left? There's going to be one that's big and one that's small. Let's just find the small one. And here's one approximation. This came later, this wasn't how old we did it originally, but one approximation is then that the eigenvalue we're looking for is the inverse of the trace of the inverse matrix. And now we can easily calculate. For a six-dimensional matrix, we can calculate the inverse easily enough, and then calculate its trace, and then take the reciprocal. Oleg did it originally by calculating the characteristic polynomial, and then saying all terms that were quadratic or higher in the eigenvalue would go away. So we only had to keep terms that were linear in the eigenvalue. And they turn out to be the same. So if we plug everything in, this is why it works. The trace of the inverse of a matrix is the sum of the reciprocals of the eigenvalues. And if we're looking for an eigenvalue near zero, its reciprocal is very large. And eigenvalues that are big, the reciprocals are near zero. So the sum of the inverses will be dominated by the smallest eigenvalue closest to zero. So actually, Hans Koss was a postdoc who realized this, and this generalizes quite easily then to more than two states, because you just have a bigger matrix to find the inverse of. So we thought we were pretty clever, and I happened to be walking down the street by Columbia's main campus, and there were a bunch of math graduate students happened to be talking about eigenvalues as I passed them. So I told them what we had worked out, and they said, of course, that's trivial. So if you do the arithmetic for the two-state case, you get this result. And suddenly, you're not sensitive just to omega E. You're sensitive to the effective fields at the frequencies of the A and B state, even though you never see the B state in the spectrum. And if the populations are very skewed, omega A and omega E are almost the same. And you get this simple result that says now you're sensitive, the exchange broadening doesn't depend on the shift that you see. It depends on the shift you don't see. And when is that going to be maximum? When is REX, as a function of omega B, when is REX a maximum? When do I see the most line broadening? What will be true for omega B? when omega B becomes 0, when I'm on resonance with the species I can't see, I get the maximum line broadening of the peak that I can see. And now we know the frequency of the minor state. There's no sign ambiguity anymore. So all we have to do is walk the carrier around until we see a maximum line broadening.
This problem you started in, what, fast exchange or
Mm-hmm.
consumption of fast exchange, and it's very analogous conceptually to something like a CEST experiment.
Well, it is the CEST experiment.
Yeah.
So because if you have the largest decay rate, you have the smallest intensity after a fixed period of time. So the CEST experiment uses a fixed relaxation delay and moves the carrier and just looks for the minimum intensity. But if you took the logarithm and divided by that time, you would have a rate, and that would be this rate. So they're the same experiment. As we'll see sometime when we talk about practicalities, there's the issue of how do you get to the prime frame. Right? This is all happening in the prime frame, the tilted frame, not the lab frame. And R1 row and the CEST experiment handle that differently. And that's the difference between the two experiments. But fundamentally, they both can be viewed as an R1 row experiment. It just depends how large your spin locking field is. Now, that
Before
is.
you leave this, I just wanted to make a comment that if you don't have some approach like this, there's a sense in which the population difference and the frequency difference are kind of entangled in the data fitting. And that's a problem a lot of the time, like what we call the order parameter could conflate both of them. And this can be a powerful way to disentangle them.
Yes.
You're getting delta omega, not just the sign, but like now you've got constraints on the population.
Absolutely. So again, being out of fast exchange provides information. In this case, we get information both on populations, but also the absolute sign. The only argument I ever won with Old is he said, why do you want me to calculate an expression for R1 row? I can simulate anything you want. And I said, maybe if we have an analytic expression, we'll get some analytic insight. And in this case, we got an analytic insight that we're now sensitive to the minor state population. But that's the only argument they ever won with them over any kind of math or physics. So this has been, these simple results have been extended over and over again. There's nice work by Baldwin and Kay. Oleg revisited it using perturbation theory. It's a really elegant paper. And can generate some pretty compact expressions. So here's the expression now. If the states, if the relaxation rates in the two states are very different, Oleg's first expression assumed that they were the same. And now here they are when they're different. The Baldwin and Kay paper does it more or less following Oleg's approach, and you get pretty complicated expressions that I can't fit on one slide. But the perturbation approach I can fit on one slide. And you can look at this. And part of the point of mathematics is to gain insight into things. If you look at this expression, you can figure out something important and qualitative about when the difference in R2s matter. And if you look at it long enough, you can see that the difference in the R2s is unimportant if that difference is less than, or the magnitude of that difference is less than the jump rate from the minor state back to the major state. So when they're important means that relaxation in the major state is faster than you jump back, which means you lose magnetization in the major state irreversibly before it can ever jump back. And then it becomes an important factor. As long as you jump back fast enough to the major state, relaxation in the minor state is unimportant. And this, in fact, is how DEST works. In the DEST experiment, the minor state is some enormous amyloid fibril. So the relaxation in the minor state is instantaneous. You never jump back to the major state. Way back early on, again, the pioneers, so then delta omega is unimportant in the DEST experiment. What becomes important is the difference between the two rate constants. And again, the DEST experiment was introduced by Floor and Nick Fauzi, but way back in the 60s, Adam Allerhan, when working out the first CPMG expressions, distinguished between what he called C and R chemical exchange effects. And C effects were caused by the jump between the shifts, and the R effects were caused by large differences in relaxation rates in the two states. So what we now call CEST, Allerhan would have called C-type exchange broadening. So maybe good that they both start with C. But what we call DEST, he would have called R-type relaxation. Very large difference in the rates in the two states. So there you go. And then, of course, if you have an approximation to the eigenvalue, there's very standard ways of improving an approximation to the eigenvalue. And Vesco Malusha, when he was in the group, worked out a second order approximation that improves on Olig's initial expression. And of course, you can do this until you get tired and decide it's better just to write a computer program. But this expression is pretty accurate. Here are some pictures. Here, if the populations are pretty skewed, black and blue overlap up here, and then Olig's approximation is quite good. The populations are highly skewed. Olig's approximation doesn't work so well if the populations aren't skewed, but the second order approximation is still very good. What's shown over here is the fast limit result. The fast limit result is always centered on the average chemical shift, which I set to 0. But here you can see the maximum is the minor chemical shift, the invisible state. And even if exchange gets pretty fast, there's still an offset. It's still possible, even for relatively fast exchange, to see the offset towards the minor state. So this is really, made the R1 row experiment and partner the CEST experiment really powerful. The main reason CPMG is used now is, I think, because it's a very easy experiment to set up. But really, the R1 row experiment is way superior as a method. Now,
Is it a question?
yeah.
Oh, so in the fastest just making sure like the faster your exchange, the larger you want.
In order to suppress the effect of the jumping, to see a dispersion curve,
Yeah.
omega E has to get to be bigger than KEX. So for faster processes, you need stronger and stronger fields. And Christian Reeser, the problem with our probe to the solution is that the Helmholtz coil doesn't generate very large fields. So Christian has had built a probe that's basically a solenoid coil, like in solid state.
Generates a lot of heat.
Yeah, well, if you work on ubiquitin, that's not your biggest concern.
Or wait.
Yes. So Christian has been trying to push these experiments down to the few microsecond time scale. And that takes very large field, which in the end you need a special probe for. Here's just another plot. So the same kind of thing, looking now at the differences associated with different values of R2A and R2B, just showing what the difference makes in the profiles. Now, I kind of said that R1 row and CES were the same experiment. But if you look at that expression, well, if you look at that expression, can you tell me why the experiment is sensitive to the Beast shift? Excuse me. When we published the paper, the next time I saw Dennis Torshaw, he asked me, "That's a nice result. Why are you sensitive to the Beast state?" And I said, "I don't know. That's what the math says." It's very hard to look at this and say, why does this experiment work this way? But of course, in NMR, it can be very useful to look at the same experiment from different viewpoints. And in CES, harking back to Hoffman and Forchen's original paper, you tend to think of the CES experiment as a saturation transfer experiment. So you irradiate at the frequency of the B state, that saturates the B state, and exchange transfers some of that saturation to the A state. And in solution NMR, kind of the Forchen and Hoffman paper was in history, and CES kind of got reintroduced from MRI, where saturation of the water could be transferred to other spins through this mechanism. But if you think of the CES experiment or the R1 row experiment in this skewed population limit, then it's clear here why you're sensitive to the omega B state, because it's also, in addition to being an R1 row experiment, it's also a saturation transfer experiment. And then you have to irradiate B state. If you don't irradiate the B state, there's no saturation to transfer. So thinking of CES as R1 row lets you write down the rate constant for the CES experiment. Thinking of the R1 row experiment as the saturation transfer experiment lets you understand why you're sensitive to the B state and not the average shift in the R1 row experiment. So it's the same experiment, but there's two different ways of looking at it. And one way, the saturation transfer view is kind of more natural if you're just programming a big matrix and having a computer solve. It's the more natural way if you want to understand why you're sensitive to the minors. The R1 row picture gives you a unified picture for all spin locks, from very weak spin locks to very large spin locks. It's the same expression, even though we call one sets and one R1 row. So it's two different viewpoints and they have their value. If you blah, 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 we can expand the matrices. It's just a bigger matrix of calculation. If we start to include things like scalar coupling into our matrices to take more and more into account more realistic spin systems, there's an important assumption. And when we write down these Bloch-McConnell equations, or their more general matrix equations, which are called the stochastic Liouville equation. And that's that when we jump from state A to state B, all that happens is we change things like the chemical shift or the R2 or the CSA, whatever. But we don't change spin states. So if we're I plus in the A state, after the jump, we're I plus in the B state. We're not suddenly zero quantum magnetization in the B state. And that means during the jump, there's no Hamiltonian strong enough to cause a change in spin states. We think of these processes as being jump-like. You rattle around in the A state, energy minimum, and then stochastically you get enough energy to jump the barrier. But you jump the barrier very fast. Right? In transition state theory, you're jumping the barrier in femtoseconds. We don't need things to be that fast, but we need them to be fast. So when you think you have a slow process, it's not that the jumping the barrier is slow. It's getting enough energy to jump the barrier is a slow process stochastically. If that wasn't the case, if we had Hamiltonians that could change I plus to S plus during the jump, this theory wouldn't work. I'm not sure what theory we would use. But fortunately, we don't have any Hamiltonians that are strong enough that we know of, bright enough. But it is an important assumption. States change the parameters like shifts, but they don't change the spin operators. They just transfer over. So that's the end for today. I was going to say you'll see them up shortly, but I'll post the paper. There is a very nice paper by Shi Zhang a few years ago, where he took one particular RNA molecule and did ZZ exchange experiments, that's population transfer of Z magnetization, R1 row experiments, and CEST experiments, and showed that all three give the same answer. So it's a very nice example, particularly for CEST and R1 row, how tightly connected they are. So I recommend that paper highly. There'll be pictures from it in some subsequent lecture, but in the meantime, I'll post it on the website so you can read it.
For the CPMG experiment, do you also want the binary state combination?
It doesn't matter there. I mean, for the R1 row experiment, the experiment itself, it doesn't matter what the populations are. It's just that these approximations require, the approximations say that there's separation between the eigenvalues. And that's guaranteed if the populations are skewed. If the populations are more equal, there may be special circumstances where the eigenvalues are separated, but you can't guarantee it. So for the analytical approximations, the populations being different is important than guaranteeing separation between the eigenvalues. But if you are programming a computer to solve the matrix equation, it doesn't matter at all.
New edition of experiment is just quickly and here.
So there's the theoretical limitation that you always only know the magnitude of delta omega. The experimental limitation is basically how fast you can do 180s. The usual theory assumes that the 180s are instantaneous. And frequently, if we're doing the experiment and we don't want to worry, we might say we don't want the duty cycle of the pulses to be more than 10%, say the delays. So we can pretend the pulses are instantaneous. If that wasn't the case, then in principle, during the 180, we should be considering the R1 row relaxation during the pulse, right? Because we've turned on the B1 field. And I think Christian Riesinger's lab has, done some work there, but we haven't. And again, I think for studying dynamics, the R1 row experiment just has a lot of advantages. Any questions online? So again, hopefully you got the email that tomorrow, Anish, there won't be a lecture. Anish is going to go over the problem that were set by Ann. So come prepared. See everybody tomorrow. And we almost have the midterm ready for you.
Oh no.
I know you're excited about that.